In the first part, we have studied the solid solution and its types. In this part of chapter, we will see next topic, diffusion in solids. Atoms have more freedom and they move from one lattice to another. This movement or migration of atoms is called as diffusion. The movement of atoms takes place from higher concentration to lower concentration. We have studied that solid solution consists of two parts, solute and solvent. During the diffusion process in solid solutions, the bonds in solvent are broken along the path of diffusion of solute atoms and which requires activation energy. As shown in this diagram, the diffusion process occurs. In the representation, black spheres are the solute atoms and white circles are the solvent atoms. The solute atoms diffuse in the solvent thoroughly. For the diffusion process in solid, it needs vacancies and interstitial voids. Diffusion mechanism occurs by following ways. First is self-diffusion. It occurs in pure metals when atoms exchanging position are of same type. Or self-diffusion is the transition of thermally excited atom from a site of crystal lattice to an adjacent site or interstice. Example: diffusion of copper atoms in copper matrix. Self-diffusion process propagates through vacancy mechanism. As shown in the diagram, in the vacancy mechanism, an atom near a vacancy move into a vacancy such that a new vacancy is created and the process continues. And then diffusion process completed. Next type is interstitial diffusion. In this mechanism, atom diffuses through solid via interstitial sites such that solute atoms must be smaller than the interstitial sites in the solvent lattice. Next point is diffusion in substitutional solution. In this type, there is a direct exchange occurs when two atoms exchange their position. Next point is factors governing diffusion. See one by one. First factor is temperature. Diffusion rate is directly proportional to the temperature. As temperature increases, diffusion rate increases. As the size of solute atoms is small, diffusion rate is high. In solid solution, if solvent having low melting point, then the diffusion rate is high. As there are more vacancies, the rate of diffusion is faster. From this, we can conclude that vacancy mechanism of diffusion is more rapid than other diffusion mechanisms. Next point is Fick's first law of diffusion. It states that the net rate of flow of solute atoms through the region of higher concentration to that of lower concentrations is proportional to the concentration gradient of diffusing solute atoms. Mathematically, it is given by dN by dt is equal to minus d dc by dx, where dN by dt is the net rate of flow of atoms, dc by dx is the concentration gradient, which is the rate of change of concentration per unit change of position. Capital D is the coefficient of diffusion. Next point is Fick's second law of diffusion, which is derived from Fick's first law of diffusion. This law is applicable for non-steady states diffusion situations. It states that time rate of change of concentration is proportional to second derivative of concentration, which is given by dc by dt is equal to capital D into dabba square c upon dabba x square. Solution to the Fick's second law given by this equation where a is the constant. Next point is introduction to error function. We have equation for Fick's second law, that is dabba c by dabba t is equal to capital D dabba square c divided by dabba x square. Solution for this equation given by c of xt is equal to a minus b error function x divided by 2 into under root capital D into t. Here ERF stands for error function, which is mathematical function given by 2 upon root pi integration from 0 to x by 2 under root dt exponential minus eta square into d eta, where eta is an integration variable. Upper limit of the integration is the quantity whose error function is required. In the figure, exponential of minus eta square is plotted against eta. The area under curve from eta is equal to 0 to x by 2 under root dt is the value of integral. The value of error function of infinity is 1 and error function for minus infinity is minus 1, and also value of error function of 0 is 0. Error function arises due to abrupt change in concentration at interface of diffusion element. Next point is experimental determination of capital D, that is diffusion coefficient. For this, consider a diffusion couple consists of two long bars welded face to face. This experiment done at various temperature so that diffusion coefficient can be determined as a function of temperature and given by capital D is equal to d0 exponential minus q by RT, where q is the activation energy for diffusion. This equation of diffusion coefficient and the equation of error function combinedly applied in many applications. First application of diffusion is to increase the corrosion resistance of duralumin. For that, we make alclad sheets. As shown in the diagram, the duralumin is cladded in between two aluminum sheets. It means duralumin core is sandwiched between two aluminum sheets. Here, duralumin is heated up to 550 degrees Celsius high temperature that enhances the strength of material. As temperature increases, copper from the inner core of duralumin is diffused to lower concentration surface, that is outer aluminum surface, which makes the outer surface more corrosion resistive. Carburization is the process of addition of carbon in steel, which increases wear resistance of gear but decreases the machinability. To balance the machinability of the gear, the decarburization of steel is done. That is, the carbon is removed from the steel. Doping of semiconductor is done to obtain desired electrical properties. Under controlled temperature and time of diffusion, the doping of semiconductor is done from the gaseous atmosphere.